Today we're going to present another way of searching a graph. It's sort of similar to BFS, but there's one key difference, and this is called depth first search, or DFS. The difference is basically in the name. In BFS, which we just talked about, let's assume we start at vertex 1. Then we're going to go to all of the ones it can go to. These are like level 1. Then we go through all of these level 1 nodes and figure out what edges does it go to. So 2 goes to 4, 3 goes to 5, and then these go to these vertices. So we're sort of processing it in order. We look at 2, 2 goes to 4, but we don't care about that yet. We're like putting that away. We go to 3 and 8, and then once we finish processing all of these, do we then go over here? And this also leads us to a tree. It goes level by level, and it has like some nice properties. For example, the BFS tree will not have an edge between something here and something like 2 levels down. And that's because if there was an edge from 2 to 6, then 6 would be in this level. To contrast, in depth first search, we start at 1, and we look at what 1 goes to. So it goes to 2, and also 3 and 8. But before we look at all the other edges that 1 goes to, we first analyze 2, and then like tunnel vision our way down here. So like, what does 2 go to first? And 2 goes to 4. And before we backtrack, we look at 4. What does 4 go to? Like 4 goes to 6. And then 6 goes back to 2, but we already visited 2. So now we're like finally done with 6. Then we go back to 4. And 4 doesn't go anywhere else, then we're done with that, and we backtrack to 2. And 2 doesn't go anywhere else, so we backtrack to 1. And then only when we're done searching this like subtree do we finally go to 3. So hopefully you guys can see the difference between these two. And again, we can think of this as being a stack as opposed to the queue. So remember in BFS we have 1, and then we added like 2, 3, and 8 to the queue. Instead, what we're going to do is like add these vertices to a stack. So we have 1, we like get rid of 1 on the stack, and we add like all the vertices that 1 connects to this stack. So like maybe 8, 3, and 2. Then we look at, since it's a stack, we don't look at the first element, we look at the last element, right? And then 2 has an outgoing edge to 4, so we put this on the stack. But instead of before, where we would like, start from the beginning, like we start from the top of the stack, which is 4, go to 6, and then so on. We like finish this before we get to the next thing on the stack. So, I mean, imagine flipping this like 90 degrees, that's like more representative of a stack, but this is the difference between DFS to BFS, right? The analogy is DFS is a stack as to, BFS is a queue. So another way of representing DFS is you're at some node, you do everything that goes out from this node, and then you like finish that, and then you finish your node. So there's sort of a time where you first visit a node and a time where this node finishes. And you could represent that in this way. Like, first I start from 1, then I go to 2, then from 2 I go to 4, from 4 I go to 6, and 6 has nowhere to go except back to 2, so we finish 6. Then 4 has nowhere to go, so we finish 4. 2 has nowhere to go, we finish 2. And you can see this as like, okay, this is my stack. It's like 1, 2, 4, 6. Then this is finished. 6 is popped off the stack. This is like 4. This is 2. And now we're finished with 2. So we're back to 1. We go to the next thing, 3. 3 takes us to 5. 5 takes us to 7 and 8, or first 7. 7 finishes. 8 finishes, then 5 finishes, and then 3 finishes, and then 1 has an edge to 8, but 8 has already been visited, so 1 is done. And another way we can visualize this, which is actually super important, is we treat these vertices as like colors. So originally everything is a white vertex because we have not explored it yet. Then once we explore a node, it becomes gray, like we're processing it. And once we actually finish it, that node becomes black. So once we start exploring 1, this turns to gray. Then 2 becomes gray, then 4 becomes gray, 6 becomes gray, then 6 is finished, becomes black. So just to sort this out, okay, we're at 1, 1 becomes gray, we visit 2, 2 becomes gray, we visit 4, 4 becomes gray, then we visit 6, 6 becomes gray, then 6 has nowhere to go, then 6 becomes black, and so on. So every time we open a parenthesis, that node turns from white to gray, and every time we close it, it turns from gray to black. Now we have this notion of what type of edge is each edge. And if we're at a vertex, we're exploring it, so it has to be gray, and we get to a new vertex, aka this new vertex is currently white, then it has to be a tree edge. So it's going to be part of our eventual DFS tree. So in this case, 1 to 2, 2 was unexplored, so it's part of our tree. Then 2 went to 4, which was unexplored, so it's also part of our tree. And 4 went to 6, which is also part of our tree. Now 6, we look at the outgoing edges, there's an edge from 6 to 2, but 2 is a gray node, which means we're currently on the path from 1 to 2, then maybe to some other vertices, then to 6. So what does that mean? It means we got to 2, we got to 6, and there's an edge back to 2. So there has to be a cycle. And we're going to call this a back edge. If it goes from our current node to a node that's still gray. And what's crucial to remember is that a back edge is equivalent to a cycle. If we run DFS and there's a back edge, that means there's a cycle in the graph. Continuing this, we finished 6, we finished 4, we finished 2, now we get to 3. So these all become black nodes. Now we go to 3, 1 is still gray. 3 is a white node, which means this is a tree edge. 3 becomes gray, 3 goes to 5, also a tree edge. Now 5 goes to 4, and 4 is already finished. So it's not a white node, so it's not a tree edge, but it's also not a gray node, so it's not a back edge. But 4 is a node that started before 5. So it was already done over here. And it's not a descendant of 5, which means we call this a cross edge. Now we go to 5, 7, and 8, right? This is a tree edge. 7 becomes gray. And now we're at 7. 7 has no outgoing edges, so it's finished. Becomes black. And then now we go to 8. This is a tree edge because 8 is unexplored. Now we're at 8. 8 has no outgoing edges. So now it's finished. We go back to 5. 5 is now finished. Now we go back to 1. And our final edge is 1 to 8. And 8 is finished. But 8 started after 1. So 8 is actually, a descendant of 1. It's not a cross edge because in this case, 4 started before 5. But in this case, 1 was our first node. 8 started and finished in between the time that 1 started and now 1 is finishing. So we call this a forward edge. So make sure you really understand how this algorithm works. Again, you're at a gray node. If you explore a white node, it's a tree edge. If it's a gray node, it's a back edge. And if it's a black node, it's either a forward edge or a cross edge, depending on if that node is part of your subtree or not part of your subtree. Here's some text that explains this again. And this exercise, which might take a long time, but will really hammer home this idea of how this algorithm works. If you want some more practice, try making another graph and running this algorithm on it. It'll be really helpful. And if this graph was undirected, why can we not have cross edges and forward edges? Well, that's because, cross edges and forward edges require you to go to an edge where this vertex is black, which means it's like already finished. But if it's finished, it's processed all the edges that come out of it. And in an undirected graph, like it'll process, this edge the other way. And that hasn't happened yet, so it's not possible that this edge is actually finished. Exercise 5 just hits home the idea, back edges go to something that's gray. And how do you tell if there's a cycle in DFS? Well, if there's a back edge, there's a cycle. If there are no back edges, there's no cycle. Hopefully that gives you an understanding of the difference between DFS and BFS, and you get a glimpse of why DFS is useful, right? Most importantly, you can tell if a graph has a cycle, which might be helpful. And in next lecture, we'll look at some more applications of DFS.